In this video, we're going to be talking about rational functions and what may happen when we try and graph them. We'll find some discontinuities, such as asymptotes or holes. We'll talk about how to find those things, but first, let's just define a rational function and see what some basic ones look like. Rational function is where we have a polynomial divided by another polynomial. We never want the denominator to equal 0. However, if it does, we're going to find out that we have some special things happening in the graph. So it's called a rational function because we have a ratio of functions. Let's look at the most basic one. This is just x flipped. It's called the reciprocal function. It's 1 over x. So we know that x cannot equal 0. That would be undefined. But we'll take a look at the graph and see that it's got a lot of other values that it could be. Here it is. We see that if we were to continue to approach negative infinity on the x-axis, that we would continue to have values that are defined. Same as if we approach positive infinity on the x-axis. But take a look here at what happens right in the middle. As x approaches 0 from the left, our outputs approach negative infinity. And as x approaches 0 from the right, our values approach positive infinity. So we can define that or describe that the following way. We can say as our output approaches negative infinity, x approaches 0 from the left. So we use this little symbol right here, this negative symbol, to describe our direction as we approach a value. We could have said as x approaches 0 from the left, f of x approaches negative infinity. Doesn't matter what order we say this in. We also said that if we approach 0 from the right, so we use a plus symbol there above our 0 to talk about our direction from the right, then our output approaches positive infinity. So we saw that happening on the graph. We can describe the domain and range, knowing that x cannot equal 0, but it can equal pretty much anything else. So in interval notation, we could describe that this way. Also, when we looked at the graph, maybe you noticed that our outputs could not ever touch 0. So that's going to be what's called a horizontal asymptote. So our range includes all values except 0 as well. So this won't always happen with rational functions where the domain and range are the exact same. It just happens in this particular example. We'll see it slightly different on the next one. If we were to graph 3x divided by x minus 1, well, just algebraically, we know that x cannot equal 1. So we're definitely going to see a discontinuity occurring there. Let's see what else is happening on the graph, though. So we can see that we have this horizontal restriction, or this output restriction right here. It's looking like it's approaching 3 but not quite touching it on either side. And then we have this input restriction where our x values seem to be approaching 1 but not quite hitting it on either side there. We could zoom out maybe if you don't believe me. So again, let's just describe that using this notation. As we approach x from the left, our outputs approach negative infinity. And as we approach 1 from the right, our outputs approach positive infinity. So we could describe the domain knowing that 1 is a restricted value, so we could have any x value or any input except for 1. And our output, any output was happening except for 3, so we could say everything except for 3 using that interval notation there. So that's the common behaviors that occur with rational functions. We may have horizontal restrictions, we may have vertical restrictions. We'll talk about it next. Anytime our graph is broken, it's called a discontinuity. We always like our graphs to be continuous, and so if they're not, that is a discontinuity. We could have lots of different ones. We're going to focus mostly on holes and asymptotes in this video, but later on, maybe at the calculus level, you'll start to see some other different types of discontinuities like jumps and other things. Let's talk about a hole first. A hole is going to be an open or undefined point on a graph. So rather than a closed shaded in circle, it's going to be an open circle at this point. They are created when we have common factors that cancel. So we'll algebraically do some factoring and cancel some common factors. The value at which you have a 0 in that factor is the value at which the whole occurs. Unfortunately, you're not going to see it on a graphing utility, but you will see errors in your data table at those values. So in this first example, anytime we're dealing with rational functions, we always want to factor first and see if anything cancels. So factoring the bottom, it's x minus 3 and x plus 2. For some reason, I forgot a little parenthesis right there. So notice that we have x plus 2 as common factors on top and bottom. They're going to cancel. They're going to reduce down to 1. But the 0 value of that factor is where the whole occurred. So the whole must have occurred at negative 2. When we write our simplified form, we have 1 over x minus 3 remaining. We're also going to see on your data table that at 3, another error occurs, but that's going to be for a different reason. We'll talk about that next. I just want to focus on wholes first here. So common factors that cancel are going to leave us with values where wholes occur. So we could check the graph, although we're not going to be able to see the whole occurring at x equals negative 2. However, on your data table, it should say, come on man, right there, at negative 2, you have an undefined output, and maybe on your data table it says error. So even though we can't see it on the graph, there is a hole in our graph occurring at negative 2. The reason why you see another 0 of the denominator there, another undefined value at 3, is because we have this vertical asymptote happening right there. But we'll do an example of that next. All right, so next example, just continue to factor top and bottom, see if there's any common factors that cancel. If common factors cancel, the value that makes that factor 0 is the point at which your whole occurs. So canceling x plus 4 means that we have a whole occurring at x equals negative 4. You can check your data table if you want to confirm that. Now, the next thing we'll do is we'll talk about what happens when we have these leftovers and we still have a possible 0 in the denominator. That's going to give us a vertical asymptote. Vertical asymptotes are going to be where our outputs approach positive and negative infinity. The x value at which our graph is doing that is going to be the value at which the vertical asymptote occurs. So in order to do that, we're just going to find zeros of the denominator. Because vertical asymptotes are imaginary vertical lines, we usually sketch them in using a dashed line, and we would write their equation using a vertical line equation, x equals whatever the value is. For example, in part A, what would make the denominator 0 in this case would be negative 4. So because we have a 0 of the denominator occurring at negative 4, that must be a vertical asymptote occurring at that value. So let's check the graph. Here we can see we have a vertical asymptote at x equals negative 4, the place where our graphs are approaching positive and negative infinity. Also on your data table, you will find errors or undefined values occurring at x equals negative 4. In the next example, we could factor the denominator here to find its zeros, or you could set it equal to 0 and solve algebraically. Getting it in that factored form, though, just allows us to see the zeros in a factored form. So x cannot equal positive or negative 3, so we must have vertical asymptotes occurring at both of those values. So we have two asymptotes here, two vertical asymptotes. Let's see if we can see them. Here's the graph of that function. Vertical asymptote happening here at negative 3, and over here at x equals 3. We do kind of see that we have a horizontal asymptote occurring, but we're not talking about that yet. We'll get there next. So again, vertical asymptotes occurring where we have zeros of the denominator. Next up, let's talk about horizontal asymptotes. These are a little tricky at first because we can have up to 3 different scenarios And so we got to be able to stay organized and know those scenarios and their results. Horizontal asymptotes, as you can imagine, I'm sure, are horizontal lines that the function typically doesn't touch or cross. However, it is true that at times a graph does have permission to cross a horizontal asymptote. Here's why. Your asymptotes that are horizontal are going to have a horizontal line at y equals whatever the value is, so just a horizontal line equation. You want to check it as x approaches positive and negative infinity. So as you go as far as you can right on the x-axis or left on the x-axis, eventually your graph will follow the behavior of a horizontal asymptote. It may not do it about the origin or close to the origin, so you got to zoom out quite a ways to see that behavior, and it will closely follow that asymptote as you go to the ends of your graph. 3 scenarios. What we want to do always, though, is compare the leading degree on our numerator and our denominator. So in this example, we have 2x to the 4th and x cubed as our leading degrees on top and bottom. Notice that the top degree is higher. So in one situation, if the top degree is more than the leading degree of the denominator, then the result is that we don't have a horizontal asymptote. So we can say it doesn't exist. That doesn't mean that we don't have other asymptotes, though. Be careful there. Just because it's not a horizontal asymptote does not mean that we don't have vertical or, as we'll see in the next video, a slant asymptote. Another thing that could happen is we could have the leading degree on the bottom be bigger than the leading degree on the numerator. And in that case, our horizontal asymptote is always going to be at y equals 0, which is just the x-axis. So you'll have a horizontal asymptote occurring at the x-axis if the bottom leading degree is more than the top. And the reason for those two things is, in one way, the principle of dominance is a thing that you can think about. So with our leading degrees or our leading terms, as our x values approach a really big number or as they approach infinity, all the other terms lose relevance. The term with the highest degree is going to dominate all the other ones as our x values get really big. And so in this example, you can think that, well, if 2x to the 4th is going to dominate everything, then we're not going to have a horizontal asymptote. We're just going to have a graph that exists. But here, if the leading degree on the bottom is bigger, then we have something similar to that reciprocal function where the x term on the denominator is going to be dominant over everything else. And so eventually we're just thinking about this behavior of 1 divided by a really big number. And the bigger number that you plug in there, the closer your output gets to being 0. So the leading principle of dominance is one way that you can try and remember which is which there. If the bottom degree is bigger, we're going to approach 0, and if the top degree is bigger, we're just not going to have a horizontal asymptote. The last thing that could happen, the last situation, is what if the leading degrees are equal? And in that case, we can ignore everything except for the leading coefficients, and our horizontal asymptote is going to occur at that horizontal line, being the ratio of the leading coefficients. So 3 situations that you got to think about whenever you're trying to decide if a horizontal line occurs and where it occurs. These are actually rules that will continue with limits. As limit values approach positive or negative infinity, you'll actually follow the exact same rules. So knowing about it now will save you a little bit of time later when you learn about limits. All right, let's see if we can put it all together, and we're going to add one more thing to it. We're going to also talk about intercepts. In our next class, we're going to be sketching the graph of rational functions. And it's going to be nice if we know where our intercepts are. Those will be some extra special points that we want to include on our graph. And it's just good remembering what our intercepts actually are, or how to find them. To find a y-intercept, we know that our x value is 0. So if we just plug a 0 into all of our x's, our output will be our y-intercept value. To find an x-intercept, we know that that's where our y value is 0. or in other words, our function is 0. And when we have a rational function, we don't care about zeros of the denominator. That's not going to be our x-intercept. We want zeros of the numerator, because if the numerator is 0, then everything is 0. 0 divided by anything is 0. So set the numerator equal to 0 and solve for x, and you'll find your x-intercepts. All right, let's find all our asymptotes, our holes, our intercepts, and we'll describe the domain. Taking this function, we're going to factor. That's usually our first step. Factoring the top gives us this result. Factoring the denominator gives us that result. We have a common factor that we're canceling, x plus 2, so the 0 of that factor, negative 2, is going to be where a hole occurs. Leaving behind x minus 1 over x minus 3, so zeros of the denominator, like positive 3, are going to be where our vertical asymptotes occur. To find our x-intercept, we're just going to set our numerator equal to 0. So we can use the simplified form of it. So x minus 1 equals 0. If we solve that, we get x equals negative 1. So our x-intercept occurs at negative 1 comma 0. Our y-intercept is going to be when our x value is 0. So plug a 0 into your x spots. Simplify and we get positive 1/3. So our y-intercept occurs at 0 comma 1/3. We know now our restrictions in our domain. We can't have x values that are negative 2 or 3, but we can have all other real numbers. So describing that in interval notation, everything negative up to negative 2, not including negative 2, everything in between negative 2 and 3, and then everything greater than 3. All right, so a lot going on there. Those are rational functions and their discontinuities, specifically asymptotes and holes. We can take a look at this graph real quick just to finish it off and check our work. Maybe. Here we go. We said that we had a hole at x equals negative 2. Looking at your data table there should tell you that negative 2 is undefined. There it is. We had a vertical asymptote at x equals 3. We had a horizontal asymptote at, what was our horizontal asymptote? Oops, we didn't find it. Sorry. Horizontal asymptote, let's take a look real quick. We got equal degrees here on top and bottom, so the coefficient is our horizontal asymptote. So y equals 1 is where our asymptote horizontally should be, and we see that occurring. X-intercepts and y-intercepts. X-intercept at positive. Why did I say negative 1? X-intercepts at positive 1. All of a sudden my algebra is horrible here. If I add 1 to both sides, I get positive 1. So good thing we checked on the graph there. Fix our mistake. And then our y-intercept is at 0 comma 1/3. Here it is right there. All right, so practice those methods because we're going to need them in our next lesson where we actually graph this all by ourselves.